Hi there, Turgeon here, bringing you physics from afar. We should always think about big questions. You should always think about why we're doing what we're doing. Before we talked about how charges were just sitting there. Now we're into the stage where we're talking about moving charges and particularly different types of circuits, different paths for the charges to flow. So here we have a series circuit path. That's where all the resistors are on one path. That means that the equivalent resistance, which is the total, is just adding them all up. It makes sense. If each of these resistances was 3 ohms, then you would look at this circuit and be like, yeah, the total resistance is 9 ohms, 3 plus 3 plus 3. What's not so obvious is the current doesn't somehow decrease as you go through each. It's just a constant current everywhere through the circuit. The voltage, though, the energy, does split up. So if this were like 24 volts, it would be 8 volts, 8 volts, 8 volts for a total of 24. So once again, the current is the same everywhere. If this were like a current of 2 amperes leaving the battery right here, it'll be 2 amperes through here, 2 amps through here, 2 amps through here. Let's look at an example. Write this example down, think about this. These will be official entries, depends on the year. This is a little complicated to look at, but I'll explain. We have a 12-volt battery, 3 equivalent resistors, all 11 ohms. I know that each voltage is going to be 4 volts because all these resistors are the same and voltage gets split up. The current's going to be the same everywhere, but how did I get 0.36 amps? That's what people are wondering when you look at that. Where'd that 0.36 come from? Well, the equivalent or total is just simply 33 ohms. We look at that and we just know for series, we just add up those resistances. To get the current, you use Ohm's law, which is V equals IR. If you plug into V equals IR, you get 0.36, 12 volts divided by 33 ohms. Use the equation. In parallel circuits, there's not just one loop, one single path. We can keep adding resistors, but we add them in a way that there's multiple paths, multiple loops. I'll show you what that looks like in a second. So what's not so obvious is that they're all going to have the same voltage, not splitting up the voltage, but they're not going to all have the same current necessarily. And the current's not going to be the same as the total. So check this out. So here I have 3 different resistors that are hooked up to a battery. What's not, I don't know if you can tell, but if you look at this resistor here, this resistor is hooked up directly to the battery. It has a direct conducting path right to the battery. So if this is 24 volts, then this has 24 volts. This has 24 volts. And I know this one seems farther away, but it also has 24 volts. They all have the same voltage because they're all hooked up directly to the battery. But if there was like 30 amps of current leaving the battery here, when that current comes to these, it splits up. That current is going to get divided up between these paths. I know that's different from series. Let's look at an example of this. If I want to find the current and voltage through each single resistor, I can tell you right away just looking at this. Take a look for a second. Oh yeah, 6 volts. Then this is 6 volts, and this is 6 volts. The voltage is 6 volts here. Now the current is a little bit more tricky. To get the current through this, I'm going to use Ohm's law for this one. Then I'm going to use Ohm's law for this one. So to use Ohm's law, write down V equals IR, plug in your voltage, plug in your resistance, solve for the current. It's 0.6 amps. Just slow down for a second and just try that. I mean, it's a skill that we've been learning since September. You use the equation. The equation guides you. The equation tells you what to do. To get the total current, it's not 0.6 amps. But Mr. Turgeon, you said that the current's the same everywhere. Careful, that's in series circuits. This is a parallel circuit. So the total current is just 1.2 amps. There's 0.6 amps flowing here, 0.6 amps flowing here. Then they flow back to the battery over here, and they rejoin in this branch, and over here they split from this branch. Now you should pause the video and try to write a few words in each of these boxes. This will also be an official entry. So for series, you can say something about the voltage. For series, you can say something about the current. Let's take out resistance, actually. Let's not worry about resistance right now. I take that out. We'll worry about that another time, maybe. Just 4. So, parallel, something about the voltage. Pause the video, give you the answer in a second. In voltage, the best word is probably splits. The voltage splits for series. The current is constant everywhere. In parallel, the voltage is constant everywhere. The total is the same as the voltage for each individual resistor. And in parallel, the current splits among resistors. There's a physics teacher right there. He agrees with me. This has been Physics from Afar.